Welcome back, everyone. I'll just make a note, there are lots of empty seats up front here. That may mean that any latecomers will find it easier to get a seat in the back if anybody feels like moving forward. Okay, so the last speaker for this session is Justin Warren, and he'll be talking about predicting the TripleJ Hottest 100 with Python. Justin is an analyst and a consultant specializing in enterprise technology, particularly infrastructure, open source software, and information security. And he works for, he runs Pivot9, based in Melbourne. Please welcome Justin.
So yes, this is me. I run a consulting company called Pivot9, and we have benefited a lot from using Python, which is one of the reasons that I came here as a contributor so that I can help get some money back into the community. And I run a blog at Eigenmagic and do podcast things, and I moonlight as a journalist as well, as we will see in a moment. If you want to find me, I'm usually on Twitter, and that's my Twitter handle. So this is about something that started probably about 4 years ago. I'm not sure how familiar you are. Show of hands, who knows about the Hottest 100? Okay, good, excellent. I'm a big fan. How many people know about the Warmest 100? Not so many. Okay, so quick explanation. The Warmest 100 was a bunch of guys based in Brisbane, I think, who figured out a way to use social media to predict the Hottest 100. So they called it the Warmest 100, and they got a bit of media. Some of it was from me. So I wrote about it and how they had predicted what the Hottest 100 was going to be. And they did it not long after voting closed. It was the first time anyone had done this. And it has been done ever since then by them and also by me. Now, they did it first, but as part of researching the story to write all of these things, I decided that I would go and re-implement what they'd done. So it was basically a replication study, if you like. So I thought, interviewing them, they told me how it worked, and I said, well, okay, I think I can do that, and I'm going to use Python, mostly. And so what I want to talk to you about is how we use the toolchain. Now that's the results that they got. So you can see it's pretty rough when you're around 80, 90, 100, and that's just because of the statistics method that we were using. It was a sampling method. There's not as many votes for number 90 as there are for number 1 and 2. You'd expect that. So the results got better and better and better the more votes we had. So that's what they did. I got involved a bit late, so I didn't have as big a data sample. So my results aren't quite as good. But they still get better and better over time. So this talk is about how I did that and how you can do it too. So the toolchain. The toolchain has basically 3 major components. The first one is data gathering, so we want to go and get the data. And to do that, we use wget. Everyone knows about wget, I assume. Who doesn't? Any show of hands of who doesn't? One person! Google is your friend. So there's also a Python library called Beautiful Soup. Particularly version 4 is the one that we were using, and I'll go into that in a little bit more detail. And the other part of it was Twitter and Instagram. So what happened was that in the first version, TripleJ had a thing where you go tweet your vote, and they very helpfully put a link to it so that you could go and share your vote with everybody else. And that went onto social media, which is public, which means anyone, me, the Warmest 100 folks, could go along and find out what everyone voted for. And we can use that as a statistical sample from the population, which we can then use to make predictions, which we did. Pretty simple, really. So the middle part is doing that data processing, going and grabbing that information, figuring out what the vote looks like, and we used an OCR tool called Tesseract. Again, I'll go into that in a bit more. And then we had to do a bunch of data cleansing. Now, this is something that you always have to do with a data analysis thing, as I'm sure many data scientists out there would know. Data is messy and horrible because the real world is messy and horrible. So you have to clean it up to make it a little bit more sensible. And then you do the analysis, which basically, there's a particular technique that I use called Levenstein analysis. That was used in the later version, and I'll explain why I chose that one compared to some other options. And a thing called multiprocessing, which I want to talk about as well, which is a Python library. Again, show of hands, who's heard of multiprocessing? Excellent, okay. The first version of this used a method that's not quite as efficient and useful as a second method, and I want to go into that. We'll explain how that works. So, data gathering. This is 2013 site of what actually happened in the votes. You can go onto the site, and as people seem to be aware of it, you go there and you select which songs you like, and it's we've picked 10 songs. You don't rank them in order, you just say, here are 10 votes for the songs that I want to be in the Hottest 100. And so we need to know, well, what are the songs that people could vote for? Because otherwise we don't know the difference between something which is a vote for songs and just some random text. So we go to the website and we use wget and or Chrome or Firefox and we screen scrape. It's pretty simple. It's largely manual actually. You can kind of script it, but it ends up taking longer to write the script than it does to just go to the page and just download A, B, C, D, and just save the HTML, which we then parse. And the way that we do that is we use a thing called Beautiful Soup. Now, it's a weird name. I don't know why they called it Beautiful Soup, but they did. And it basically is just an HTML parser. It turns some HTML, and this is the sort of function that I used. This is, I think, 2012, 2013. This is the function, or part of the module and parser that just goes to the HTML, grabs the bits that we need, which is the song name, the artist name, and a couple of other bits of information that are useful. In this case, the link and the track URL that it came from. And we just chuck that into a CSV file, which it then dumps out to disk. That's basically it. Then we want to go and find the information on the votes. Now, the first year it was really handy because TripleJ used a thing called TripleJ Gadget. And that would go into the URL when you went share, and it was a lovely filter string because it was the only thing that was going to have that thing in it. Otherwise, everyone was going hashtag hottest 100, and that had all sorts of other nonsense and noise and craziness. This was lovely and clean. So that made it really easy, and there's a thing that you could just grab off with pip called Twitter, which just calls the Twitter API, gives it a lovely Python thing, and login and password, which we don't use anymore, but when we did this in the first year, it was that easy. Put in my login, my password, and scrape. Sleep one, go and fetch another vote. Put it into a file, and voila, we've got all the things. Instagram was a bit trickier. After the first year when they changed this, then they didn't have these lovely links back to people's exact votes. So we had to figure out a different way of doing it. Turns out people really like the Hottest 100 and they like to share. So what they would do is that they would vote, and then they would go and put it up on Instagram. And it would look something like that. I think this is 2015 is the vote. But this is basically what it would look like. One frustration would be that TripleJ would keep changing what this looks like. So that made it, you had to adapt things from year to year. But that's what we would go and grab, and that's the image which we would then need to go and process. So we data gather using Instagram API. In this case, you go and use an access token, which means you have to log into it. You have to have an Instagram account. You set up, this is an application. You run through the standard thing. There's documentation on their site for how to do that. You put in an access token, which I've very cleverly not put in here so that you can't go and use my account. And then you just go and say, right, find all the recent tag media with that hashtag, hottest100, and everyone who has tagged their Instagram photo with hottest 100, and you get all of their photos. Not all of them are votes. Some of them are photos of people having a hottest 100 party. Some of them have nothing to do with hottest 100 at all, which is bizarre and weird. Again, real life is messy, data is messy. wget, 41 in whatever 1,000 URLs we have, go and fetch the image and save it to disk. Then we do the data processing. Now, there's a great library called Tesseract. Well, it's not really a library, it's actually an application. It's written in C, I believe, but it is available in GitHub. Oh, Octocat doesn't show up well on black. I'll have to remember that. Sad face. It's better over here. He's weird shades of black. Or she. Is it a he? Is it a she? I don't know. Yes. May not be either. So we use Tesseract. It's an optical character recognition piece of software. So it will go and look at that, and like you and me, it will figure out what is a character and what isn't. And then it will spit out something that looks a bit like this. As you can see, it's not perfect, because that sort of thing is a bit weird, and depending on what font's used and how good the resolution is and whether they've added some fancy filter or not, can mean it's a bit hard for Tesseract to read it. You can tweak some of the settings to say this is the character set that you should use, You know, it's in English, it's not in French, so don't go putting e-acutes all over the place. It's still not perfect. So we have to go and clean it up, and some of the time it was just easier to just find some regular expressions for common mistakes that it would make and just go and replace them with something else. Again, we weren't trying for perfection, we were just trying to get good enough. And that was good enough. Then we do the data analysis. So we had to go and figure out, when we have a string like that, does it match this? Probably. We would look at that and go, yes, yes it does. Computers are really stupid. And they have no idea whether that matches or not. So we have to kind of figure out, well, how do you decide that that string is similar to this other string? Turns out that's actually pretty tricky to do. And you don't really think about it until you try to write a program that says, well, how similar do they need to be for us to decide that, yes, that is the same? So the first way I used, which I don't understand, but it's a library that does this, which is called nilsimsa hash. Basically, it was designed around email so that you could figure out, is this email similar to this other email by running a hash function over it? And it sort of looks like this. So you have right and left, so comparison left, comparison right. Do nilsimsa on it. So it does some magic statistics things and says, okay, we've got those two, and then we do a hash of them, and then we compare those two hash. So it does a hash digest. But it's not like SHA-1 or MD5 or other hashes that you're probably familiar with, which are one-way hashes that you shouldn't be able to come back the other way. How many people are familiar with that kind of crypto hashing thing? Yes, okay, good. This hashing is not designed to be one way. It's designed to come out with, if you have similar input, you should have similar output. And it's similar in a specific way. So then you can say, if sim on this is similar enough, which you set as a function, then it will work. It will say, yes, they're similar enough. That is the vote that they had. Levenstein distance is different. What this does is it tries to figure out whether or not the two strings are different. It basically says how many characters in this string would need to change for it to match the other one. So dog and cat are both 3 letters, but you won't have to change many letters to make them be similar, whereas cat and character-based string difference are quite different because there's more characters in it. So it actually works better than nilsimsa hash. Again, I don't really understand the maths behind it. It's a library. I just use it. You know, import teleportation. It's great. Python's awesome for that. So what you do is you say, well, in this case, it was a key and a new key, which is just the code that I was using. Basically, it says, here is the tesseract key. Here is the actual key that we think it should be, because I'm doing a for each song in the entire corpus. How similar are they? If they're similar enough, which is the threshold, which is a dynamic parameter, you tune and muck around with it a few times to test what worked. And if it is, then yay, match. 1 vote. And then we do that for, I think it was about 5,000 or 6,000 different files and all of the different thousands of songs. And it's great because my laptop has an i7 in it, and it does this really, really fast, which is great. How? Multiprocessing. If you do it one at a time, and you've got several thousand of them and all of the different combinations, that's really slow, as it turns out. Multiprocessing is less slow. That is not to say that it is fast, but it is less slow. There are also slower and less slower ways of using multiprocessing, as it turns out. Now, the kind of obvious way to use multiprocessing is to use chunking. That was the way I did it at first. So it's a bit like MapReduce. We have this entire list of possible vote things that we need to go and process. So all of those files over there and all of these. I have 8 CPUs in my machine that I can use. So let's divide up the work and say, right, the first person can use, so MapReduce, the first one, his CPU 0, you can have this many. So let's say we've got 10,000, CPU 0, 10,000, let's do this easily. We'll say there's 5 processors, because I don't like maths. And then we can say, right, you get 2,000, CPU 1, you get 2,000, CPU 2 gets 2,000, and so on and so forth. So everyone gets the same amount of work. That should work really nicely and have nice even load balancing, yes? No. No, it doesn't. So you do a chunk size like this, and that's basically what it was. Chunk list, chunking function, which doesn't exist. You have to go and write one, which is kind of frustrating. But yeah, for enumerate. Create a process, which is multiprocessing, run it on a separate process so it ends up on a different CPU, and run them, and then there's some other mechanics that you need to do at the end to join it all together. But that's the theory. What actually happens is that CPU 0 does this kind of work. So in that case, the first set of processing of Tesseract takes that long, and then the second one takes this long, and then that one, and so forth. So the total runtime is that much. And then CPU 1 does that. So it spends a whole bunch of time not doing anything because it has no work to do, and that's not very efficient. And then CPU 2 does the same thing, and CPU 3 does that. It's no big deal if it's only a very short runtime, but if we're talking about 30 minutes worth of analysis, that's kind of lame, because you end up doing, the last CPU ends up running for like 2 minutes because it's got all of this extra work that everyone else is finished and sitting around waiting. And who's seen that lovely animated GIF where CPU 0 is doing amazing breakbeat and breakdancing stuff while all the other CPUs sit around going... I should have found it for this talk, but never mind. It's very cool, you should look at it. So what we do instead is we use worker pools. This is much more efficient, as it turns out. So what you do is you say, you init a pool of workers, and you say, well, I'm going to have a pool of about 8 workers because I expect that the maximum number I'll need is 8. That's how many CPUs I have. And you put them into a pool using multiprocessing. Fun fact, when you init worker, you have to put a signal inside the worker to say, I need to, if I hit Control-C, stop, because otherwise it would keep running and do stuff forever. And that's bad, because you'll realize after you've hit enter that you say, actually, that parameter's wrong. Oh, damn. Now I have to wait 30 minutes for it to finish. Or Control-Z and kill stuff, and that's evil, and we shouldn't do that. Also, fun fact, Stack Overflow is great. I wouldn't be anywhere near the programmer I am without Stack Overflow. How many other people are cut and paste programmers? Yeah, it's way easy. You have to do a wait, you have to do a get, otherwise it won't let you Control-C because reasons. So the way we use it is in our pool, we apply async, which is find match, which is the function that we define to say, right, go and find out with that Levenstein distance for X in vote line, so all of the votes, go and analyze that by trying to find a match and do it with a pool. So what that does is it says, I have work and I will allocate the next piece of work to whoever is free. So that way your workers, when they're not busy, they sit there waiting for another piece of work. If there's work to do, they get given a task. And then when everyone is idle, means that there's no more work to do. So you get nice, easy performance, and everyone stops working when all the work is done. Nice and easy. Then we do the last bit, which is spreadsheets and graphs and statistics, and it's loads of fun. It's good. This is the cool piece. So that's what happens. We have the song, and then we have, this is the official rank. That's what actually happened in, when was this? 2013, I think? Last year. Ah, the latest one. There we go. 2014. 15. What year is it? 2015. It was the 2015 results, which happens in 2016, because, yay, calendars. And so that's what actually happened, and then there's a couple of different models, which is basically we change the Levenstein distance in, okay, how close a match do we think it should be, and some other things around groupings, and do we consider every single vote being a vote, or do we have to have someone has voted for 10 songs is a vote, and they give you slightly different answers. And this tells us how wrong were we, because all models are wrong, but some are useful. And that tells us, okay, that's roughly how wrong we were. The average error was 98. That's not so great. The average error on the other one was much better. Hooray, better model. And then you can draw a picture, which shows you how wrong you are based on how far away you are from 0, or 1. So number 1 rank, it's a very small error. This one here, this is fascinating. I can't remember exactly which song it was. It might have been Drake Hotline Bling or something. It was, one of them was a bit strange. There was a song here that the model said, like, we should be getting more and more accurate. That's really, really inaccurate for this far down in the count. That's a bit sus. Who remembers when Tay-Tay was not allowed in the Hottest 100? I do, yeah, that was banned. This is weird, because that shouldn't have happened according to the model. That tells us that there's a song in there that TripleJ says this was super popular, and the model says, nah, no one was voting for that. Why is it so high? So there's either something wrong with the model and the data collection, which is bias, and that could be happening, or there could be shenanigans. We don't know, because TripleJ never tells you anything, and it's not audited. It's not a real competition. Shh, it's not real. It's all fun. It's just fun. No one would take this seriously, or it wouldn't affect anyone's ability to earn money or anything, would it? Oh, hang on. Yeah, fun fact. The very first time this was done, when the Warmest 100 came out, it was just after voting closed. Yes, but it was before betting had closed. It took Sportsbet 3 or 4 hours to figure out that this had got out. This is for next year. So if you win, Flume to win. There you go. So you can bet you can make 400% on your money if you're right. We don't have any data yet, but this shows you what you can do with social media and a few Python scripts. And that's pretty much all I had to talk about. Questions?
Thanks very much. Are there questions? I've got a question.
Okay.
Did you consider looking at the betting odds and incorporating that into your predictions?
That would have been a different prediction model. So that's a different kind of things. That's what people do. Like 538 does that, which is it's kind of a meta model.
Yes.
So you're basing it on other people's things. That would be an interesting exercise to do, but we're trying to do direct sampling of the population rather than a betting is what other people think is going to win. It's usually good if you have a pretty good thing, but when it's wrong, it's really wrong, as we found out from the last election. Yeah.
Thank you. Were you aware of the difflib stuff, and if so, how that compared to the Leviathan distance?
I think so. From memory, I did look at it, but there was some reasons why it looked a bit more complex, and partly it was just I didn't really understand it in enough detail. And honestly, last year it was in a real hurry, and we did this in about a week. Chris helped me out quite a bit doing some checking of what we'd done around the models, and Chris actually did some way more complicated Monte Carlo analysis, which is very cool, but beyond what I understand. So annoy him about that sort of thing would be good. I think I just dobbed you in a bit. Another one? I will have to check it out for next time, though, so thank you for reminding me.
Was it just Twitter that you scraped for the data, or were there other sources as well?
The first year was just Twitter. The second year, second and since then has just been Instagram. I did have a quick look at Facebook, but again, I ran out of time to actually figure out how to do the interface and then make it in the same sort of format that it would fit the toolchain. Having more diverse sources of input and having a bigger sample set absolutely should improve the results, yeah. Snapchat's probably not a bad place to go and get it, although you can't actually see them after they've gone because they've all been deleted. Yeah. Sure they have.
Okay, thanks very much for an excellent talk, and
Cool.
I'd like to present you with a PyCon mug.
Cool.
Can we just thank Chris once? Sorry, not Chris, Warren.